Hi everyone, Dr. P here again, and in this lecture video we'll take a look at the final type of pericyclic reaction, that is sigmatropic rearrangements. Now, you won't need to know for this class any Woodward-Hoffman rules for sigmatropic rearrangements. They do exist. They are more detailed. They are not more detailed, but they involve some additional concepts that I really don't think we need to go into. In fact, if you've read chapter 30, you've probably noticed that my Woodward-Hoffman rules, or the Woodward-Hoffman rules that I gave you for cycloadditions, are a little different than what is mentioned in the text. So if you are reading the text and you notice the terms suprafacial and antarafacial, just don't worry about those. Okay, so we won't deal with those. So what do I want you to know about sigmatropic rearrangements? Well, I want you to be able to identify them. Remember, way back when, in lecture 1, we saw that there was a change of gaining 2 sigma bonds and losing 2 pi bonds for cycloadditions, gaining 1 sigma bond and losing 1 pi bond for electrocyclic reactions, and no change in sigma, the number of sigma or pi bonds for sigmatropic rearrangements. So I do want you to be able to recognize sigmatropic rearrangements. So let's look at a few examples. One is a 1,5 sigmatropic rearrangement. And an example of this is the 1,5 hydrogen shift. Notice I said a hydrogen shift, not a hydride, although the hydrogen is bringing its electrons with it. So let's go ahead and draw out a molecule here. Boom, boom. So I've got 3 hydrogens here, so I'll just draw one of them. And so what's going to happen is we will get our hydrogen jumping over, forming a new single bond, sigma bond, with that carbon there, while these pi bonds kind of rotate around. And of course that sigma bond breaks. Typically we'd heat these. You could use UV light. It changes some of the, can possibly change some products, but we're not going to worry about that. We're just going to focus on recognizing what's going on. Now, I call this a 1,5 hydrogen shift. Why is that? Well, let's see. What's going on? Where's my new bond forming and where's my bond breaking? Okay, so there and there. So if I cover up the rest of the molecule and just look at what's on one side of the bond breaking and forming those bonds, I can number my atoms. I have 1. And then if I look at the other side, I've got 1, 2, 3, 4, 5. So if I'm looking at, where my bond that's breaking is and my bond that's forming is, and I go with the atoms in a ring one way, I get 1, 2, 3, 4, 5, and atoms in a ring the other way, well, there's only 1. So that's where I get 1, 5 from. It refers to the number of atoms in the ring there. All right. What else? We can have some. We could have 3,3 sigmatropic rearrangements. Here's one example, which is actually, I think, the example that I gave I gave before. So I'll go ahead and we'll get electrons moving there and moving there. And now I get boom, 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 boom. All right, there we go. And if I number these, so this is new bond forming, bond breaking. So I've got 1, 2, 3, and 1, 2, 3. So that's where I get 3, 3. So 3 atoms, 3 atoms. This is called the Cope rearrangement. We can involve atoms other than carbon. So again, if I heat this guy up here, I can get my electrons moving around, and then what I'll get is that product there. This is called a Claisen rearrangement. Now notice that I tried to draw my equilibrium arrows uneven here. The product in both of these is more favored. So you get about 85% product in the Cope and 90% product, versus 10% reactant here in the Claisen. So when we're looking at these types of rearrangements, the rearrangements will typically occur when the product is more stable than the reactant. So if we look here, we have monosubstituted alkene, another monosubstituted alkene. In the product, we have one monosubstituted and a disubstituted transalkene. That's more stable, so the right side of our reaction here will be favored. Over here, we have two alkenes versus an alkene and a carbonyl. And the carbonyl is actually a stronger bond. The CO bond is a stronger bond in terms of bond dissociation energy than the CC bond is. So that explains why this product is favored, because that's a stronger bond. It's kind of weird how it's a stronger bond and yet it's more reactive to certain things. Well, that's due to the polarity, and we've seen that to some extent, and we'll talk more about that in a few more chapters. Anyway, going back and looking at the 1,5, let's see if we can figure out which side would be favored equilibrium-wise. So I've got a disubstituted, geminal disubstituted, and a cis disubstituted. Here I have a tri-substituted and a monosubstituted. So I really have no idea which way this is going to go. You may end up with more like a 50-50 mix. All right, so these are types of sigmatropic rearrangements, these are some of the more common ones. And again, I'm not going to go over the Woodward-Hoffman rules for sigmatropic rearrangements. They're kind of outside the scope of this course. There's a reason that McMurray put the pericyclic reactions in chapter 30 at the end, is that a lot of courses don't even mention anything other than the Diels-Alder reaction. So, we do like to talk about electrocyclic and sigmatropic rearrangements, but not in nearly the level of detail for sigmatropic that we do for the others. So you guys don't have to worry about molecular orbitals for the sigmatropic. Just be able to recognize them. All right, well, that wraps things up for chapter 30. Go ahead and take a look at the practice problems. I'll have a practice quiz up soon, and yeah. In the meantime, stay safe out there. Bye now.